Linear and logistic regression are some of the most commonly used methods in applied statistics and data science. For the newcomers, though, a question that doesn't get asked nearly enough is when and why you should use these methods in the first place. Well, keep watching because we're going to talk about that. Hello again, everyone, and welcome back to my channel. If this is your first time here, my name is Richard, and this is RichardOnData, the channel where I help you break into data science and grow your skills in the field. So I know this happens because I saw it myself in academia, but a lot of people will start out by learning regression through the math and the matrix interpretation. The estimate of the slope vector is equal to the inverse of x transpose times x, then times that by x transpose times y. Interesting. I'm not knocking understanding that by any means. That's not what I'm trying to do here. There is a tremendous amount of value that comes from understanding the mathematical underpinnings of regression, or quite frankly, from any model you choose to use. But you'll quickly find yourself in a situation where you're trying to solve a real-world problem for a client, and you don't want to catch yourself asking, is regression truly the best way to attack this problem? So I'm going to give a super brief overview of what linear and logistic regression are, broaden that discussion to supervised learning and what the goals of these types of exercises are in the first place, and then how you should think through these problems and how to attack them. Before I do that though, subscribe to my channel if you haven't already, hit the notification bell, and smash the like button for the YouTube algorithm. Then if you guys would like to support my channel above and beyond that, I'll have links in the description of the video to my PayPal and Patreon accounts, as well as to my crypto wallet addresses. Your support is highly appreciated. Alright, so let's start off with what the regression methods even are in the first place. And if you're familiar with this already, feel free to skip ahead in the video. But let's start from the premise that we have a data set that's in tidy format. That is, every cell contains a value, every row contains an observation, and every column contains a variable. Then let's suppose we have one variable that represents some kind of outcome or response that we're interested in, and we're typically going to represent this with the letter y. Now that outcome variable might be continuous or discrete, and if it's continuous, then you're looking at a linear regression problem. If your response variable is discrete though, well then that gets a little trickier. Suppose your response variable has two distinct levels. Often then we'll just call one of those levels success and the other failure. And under those circumstances, your data set is a candidate for what's known as binomial logistic regression, which is often just referred to simply as logistic regression. We'll cover that more in a little bit here. Granted, if that response variable has more than two levels, you have extensions in multinomial logistic regression, and there are ways to approach that problem depending on whether those levels are nominal or if they're ordinal. But anyway, back to the whole rest of the data set. So for all the rest of the variables, there's a lot of names we can call those. Explanatory variables, features, covariates, predictors. My favorite term is predictors. Also, let's refer to these as the X's. And in fact, for now, let's just suppose we have two variables, the response variable y and a predictor x. And for this example, we're going to use the super basic MPG dataset from R. Well, suppose you want to understand the relationship between these two variables. The first thing that you're probably going to want to do is create a scatterplot of them. So you end up with something like this, and you very quickly get the general idea that as the x variable, displacement, increases, the y variable, highway miles per gallon, decreases. You can also generate the correlation coefficient, which is one of the most frequently used metrics, even if it's not the most interpretable in and of itself, and it's negative 0.766 here. So already we're beginning to learn a few pieces of information about the relationship between the y variable, highway miles per gallon, and the x variable, which is displacement. A regression model is going to formalize our understanding of this relationship. You fit a linear regression model, generate output like this, and suddenly, yes, our understanding of that relationship is formalized, and we have tangible information that we can take away. For example, most importantly, the estimate of the slope parameter on displacement is negative 3.5306, meaning for every 1 unit change in engine displacement, we expect highway miles per gallon to decrease by 3.5306 units. And then also multiple r squared is 0.5868. Meaning 58.68% of the variation in highway miles per gallon is explained by this model, specifically the linear relationship on engine displacement. So that super simple model was created by, like all regression models are, through the concept of least squares. That is, by finding the line that minimizes the sum of the squared residuals. Residuals being the difference between our observed values, that is the y, and the fitted values. Let's call that y hat. So we can take this same concept and essentially project it into multiple dimensions, where the effects of multiple different variables on the response are analyzed and controlled for. For example, this model where, once again, the response variable is highway miles per gallon, but we also introduce a variable for the number of engine cylinders, the drivetrain, and class of car, on top of that displacement variable that we had in the model before. Suddenly we have a lot more information. Let's take, for example, the variable class. Now, this is a factor variable that estimates the effect on highway miles per gallon for different classes of car. Now, all of these are relative to some baseline. Now, you have to do a little bit of digging through the data set, and you find out that the baseline is a class of 2-seater. So holding everything else constant, a compact class is expected to have a highway miles per gallon of 3.8536 less than a 2-seater. Plus, also of interest is the fact that the estimate for the slope parameter for displacement has changed around a lot. Recall in our previous example, it was negative 3.5306. Now it's negative 0.3203. So there you go. Are you getting the idea so far that linear regression really helps you understand relationships and how a particular variable of interest affects some response variable? And then we don't have to repeat this same exercise for a logistic regression because essentially you get the same information from that. But I'll have a link in the description of this video to an R tutorial I've done where I basically interpret every single piece of output from both linear regression and logistic regression. But in short, you get to understand how the log odds of the outcome, that is the natural log of the probability of success divided by the probability of failure, changes with various predictors. Very similar premise to linear regression, even if the mechanics are a little bit different. Now I want to take a moment, zoom out to 30,000 feet here, and look at the broader type of methods that linear or logistic regression fit into in the first place, and what the overall purpose of any of these methods can be. Regression models are a type of supervised learning method. Now, what is supervised learning, you might ask? Well, broadly speaking, it's any type of problem where you have the kind of data set I've described up to this point. That is, you have a response variable and you have a set of potential explanatory variables or predictors. Contrast that with unsupervised learning, where there is no known response variable at all. And often in those types of problems, our goal is dimensionality reduction, so we might use a technique like principal component analysis. But probably more often, our goal is to create our own classes or clusters. So when you got one of those supervised learning problems and you have a fully defined response variable, well, there's really two types of things you might want to do here. And those are inference and prediction. I've done a whole video on the difference between these two where I really go into detail of examples of them. You can find that in the description, but I'll briefly go over the difference here. If your goal is inference, then you want to infer how the various predictors, or often just one single predictor, influences the response variable. You want to understand that relationship or those various relationships as best as possible. So you probably care most about maximizing the goodness of fit of the model. And there's various metrics for that, such as adjusted R-squared, pseudo R-squared for logistic regression, AIC, BIC, the list goes on and on. Whereas in the case of prediction, that's when you want to build a model that can, with the most accuracy, predict the response variable. Suppose you were given a brand new data set where you knew all of the predictors, but the response variable at that time was unknown. Well, then you would want to be able to take your model, run it, and get as close to the true response variable as possible. There's tons of real-life scenarios where that kind of thing applies. Now let's suppose you have a continuous response variable. Your goal is probably going to be to minimize a metric like root mean square error. Granted, you may run into circumstances where predicting too high is worse than predicting too low, or vice versa, but that's usually the kind of approach you're going to take. If your response variable is categorical, though, that gets a little bit more complicated and nuanced. Now, I talk about these considerations in my R tutorial series on Caret. That'll be in the description too, but still, this is broadly a whole separate video topic. You'll notice that almost everything I've described so far about what a regression method has going for it pertains to inference specifically. That really is where regression methods shine. They dissect the variation in the response variable in linear terms and are easily interpretable. You could say that they're so simple, even your clients will understand them. But these and other statistical methods aren't necessarily designed for prediction. And yes, there usually is a trade-off between inference and prediction. Granted, it's difficult to find studies or rigorous analyses on this because every problem is a little bit different, but it's generally agreed that machine learning methods that rely on novel algorithms and detect complex patterns, for example, neural networks, are going to be superior for predictive purposes. Now, there is one possible approach to regression that sort of strikes a balance between the two goals, though, and that's regularization. Specifically, the two most common ways we can skin this cat are L2 regularization, also known as ridge regression, and L1 regularization, also known as lasso regression, or just the lasso. This is another topic for which I could do a whole separate video on the distinction between these two, but I'll try to boil it down as simply as possible. In essence, there is a penalty in both of these for having too large estimates of slope coefficients. As your slope coefficient estimates increase, that leads to high variance and overfitting, and you're trying to correct for that by introducing some bias. And the single most important distinction between these two methods is that the lasso can actually reduce your slope estimates all the way to 0. Remember that if the slope representing the rise in the response over the run of the predictor is 0, that predictor is essentially useless because it means there's literally no linear relationship between the predictor and the response. So the lasso is actually helping us perform feature selection and even get rid of some variables in our model. Ridge regression, though, doesn't do that. You may end up in a scenario where your slope coefficient estimates are going pretty close to 0, but they're never actually going to go all the way to 0. So ridge regression does not double as a feature selection approach in the way that the lasso does. So if you take either of these two regularization approaches, you'll finish up and you have a regression model still, and it's probably going to perform a little bit better for predictive purposes, but you've lost some of that beauty of interpretability that comes with the ordinary least squares solution. And that's because you have biased slope coefficient estimates now. How exactly are you going to interpret those and explain those to people now? Not to mention that if you're using the lasso, you might have even dropped off one of the terms that you wanted to understand more about the way it influences the response variable in the first place. So you see, this is all a trade-off, and it all comes down to understanding what the purpose of your analysis is in the first place. One final idea that I'll leave you with, though, is that you don't have to be monolithic. For the same analysis or exercise, you can try multiple models. And in fact, when the goal is prediction, it's perfectly common to ensemble predictions over multiple different classifiers or multiple different models. But even for inference, every algorithm is different, and every practitioner is painfully aware of all the assumptions that linear regression carries. For example, normality and constant variance of the residuals, truly linear relationships between the predictors and the response, and you have minimal multicollinearity. You should probably check these things out, especially if your goal is inference. But you can tell a very interesting overall story if on top of a regression method, you also use some other statistical method or machine learning method that can be used in and of itself to tell an inferential story. If you've got the same covariates that are super important, both based on the absolute value of a t-statistic from a regression method, as well as the mean decrease in Gini index from a random forest, you've probably got yourself a pretty robust result. But if these things tell wildly different stories, it couldn't hurt to try to understand or come up with a hypothesis for why that is. To summarize this whole discussion, I personally love regression methods and I use them all the time, especially when I'm trying to create a baseline for predictive performance to see how much better machine learning methods are doing, or if I'm trying to tell a story to my client about how one predictor or multiple predictors exactly influence some response variable. But don't make regression methods an exercise in trying to fit a round peg into a square hole. Use them with intentionality for the right kinds of problems. So thanks for watching this video. If you enjoyed it, please consider sharing it, smash the like button, and also leave me a comment down below and let me know, do you like regression methods yourself? Do you hate them and you're all in on machine learning? Let me know what you think. Then I'll see you all in the not so distant future. Until then, Richard on Data.